Stretching across the night sky, the Milky Way holds billions of stars and countless secrets that quietly surround us. Tonight we'll share the most relaxing facts about our galaxy to help you drift into calm sleep. If you enjoy this peaceful journey, please like, subscribe and share, and tell us in the comments, where do you usually watch the night sky from? Thank you for joining us now. Let's begin. Far beyond the bright disk of the Milky Way, where the galaxy's light fades into the dark, an immense halo of stars surrounds everything. It stretches for hundreds of thousands of light years in every direction, a sphere so large that the spiral arms themselves seem like a small internal structure nested within it. Here, in the outermost domain, the density of matter becomes exceedingly low. Individual stars drift in wide, slow orbits that take billions of years to complete. The light of these ancient suns is faint, scattered thinly across the sky, forming a diffuse and ghostly envelope around the luminous disk below. These halo stars are among the oldest in the galaxy, forged when the Milky Way was still assembling from smaller fragments. Their motions are uncoordinated, moving not in a single flat rotation, but in random paths through 3 dimensions like slow sparks, moving through a vast invisible ocean of space. Many are poor in heavier elements, meaning they formed before earlier generations of stars had seeded the galaxy with metals. Their light, though dim, carries the memory of a time when the galaxy was young. Embedded within this quiet halo are nearly 200 globular clusters, tightly bound groups of hundreds of thousands of stars. Each cluster orbits the Milky Way on a long elliptical path that can take it far above or below the galactic plane. From a distance, these clusters appear as compact spherical clouds glowing faintly with the combined light of countless aged stars. Inside them, stars are packed closely together, separated by just a fraction of a light year. Yet even within such density, their motion is slow and orderly, bound by the gentle balance of gravity that has held them intact for over 10 billion years. Many of these clusters formed before the Milky Way itself took on its current spiral shape, and their orbits trace the galaxy's deep gravitational well. Each cluster acts as a quiet time capsule containing stars whose chemistry reveals the conditions of the early universe. Floating even farther out are the Milky Way's small satellite galaxies, faint companions that orbit the larger spiral much as the Moon circles Earth. The most massive of these are the Large and Small Magellanic Clouds, irregular dwarf galaxies visible from the southern hemisphere. They drift around the Milky Way in wide looping paths connected to it by long filaments of hydrogen gas known as the Magellanic Stream. These flows stretch across hundreds of thousands of light years, shaped by gravitational tides between the galaxies. The stars within the Magellanic Clouds are younger and richer in heavy elements than those of the halo, hinting at ongoing cycles of star birth and gas exchange. Smaller companions such as the Fornax Sculptor and Draco dwarfs are dimmer and more ancient, their stars faintly glowing at the edge of detectability. They orbit in a loose system, forming a miniature cluster of galaxies that moves in harmony with the Milky Way's own motion through space. Between these companions, an even fainter population of stellar streams winds through the halo. These elongated ribbons of stars mark the remnants of ancient dwarf galaxies and star clusters torn apart by the Milky Way's gravity. The Sagittarius stream, for instance, wraps almost completely around the galaxy, the residue of a small galaxy that is gradually being absorbed. Over immense timescales, such mergers build up the Milky Way's mass, blending the stars of smaller systems into the smooth, diffuse glow of the halo. Yet despite the slow violence of tidal forces, the overall effect is tranquil when viewed from afar. The streams move so slowly that their shapes change only over hundreds of millions of years. It is a realm where gravity acts not as a force of chaos but as a patient sculptor, blending and smoothing the faint remnants of earlier epochs. The halo itself is not entirely visible to human eyes. Most of its matter exists as dark matter, unseen yet measurable through its gravitational influence. This invisible component extends far beyond the limits of the stellar halo, perhaps to a radius of several 100,000 light-years. Its presence ensures that the galaxy's outer stars remain gravitationally bound, even though the visible mass alone would not be sufficient to hold them. In this way, the dark halo acts as a silent framework stabilizing the slow rotation of the entire system. Around this framework, the Milky Way and its satellites move together through intergalactic space, each following the deep contours of gravity. The outermost regions merge gradually into the intergalactic medium, where the galaxy's influence fades and the pull of distant systems begins to balance it. Within this enormous halo space is profoundly quiet. The density of gas is so low that collisions between particles are rare, and light travels largely unhindered for vast distances. Cosmic rays and magnetic fields drift through in faint currents, but the dominant feature is emptiness. Stars here are separated by tens or even hundreds of light years, making the night sky from any one of them sparse and dark. Yet it is this emptiness that gives the halo its serenity. With so few interactions, the stars retain their slow, steady courses. Over billions of years, their paths form a gentle web of motion that changes almost imperceptibly with time. Seen from the galaxy's edge, the Milky Way would appear as a luminous spiral disk enclosed by this pale, diffuse sphere. The halo's faint light would blend softly into the cosmic background, a whisper of starlight surrounding the brighter core. The satellite galaxies would appear as small companions moving in stately loops, their orbits so extended that they would require entire ages to complete. It is a scene of stillness on an unimaginable scale, a system vast beyond comprehension, yet held together by the simplest physical law, gravity drawing mass toward mass. For observers on Earth, none of this structure is visible directly to the naked eye. The halo reveals itself only through careful measurement, through the faint shimmer of distant stars and the precise tracking of their motions by instruments like the Gaia spacecraft. Over time, these observations have traced the slow architecture of the galaxy's outskirts, showing how its components move in harmony. The result is a picture of immense calm, a vast balanced structure suspended in darkness, where each component from the faintest star to the largest satellite contributes to the Milky Way's quiet gravitational symphony. Nothing in this outer realm moves quickly. Each orbit unfolds over epochs measured not in years but in billions of years. From this tranquil sphere, the spiral disk glows faintly in the center, slowly turning while the halo stars continue their patient drift. This is the boundary of the Milky Way, an invisible frontier defined not by walls, but by the gentle fading of light into the silence between galaxies. Encasing the luminous portions of the Milky Way is a vast invisible sphere made almost entirely of dark matter. It cannot be seen or touched, yet its presence defines the shape, motion, and stability of everything the galaxy contains. Astronomers infer its existence not through direct detection, but through the way stars move. The galaxy's outer regions rotate faster than they should, if only visible matter contributed to gravity. This discrepancy reveals a hidden mass surrounding the disk, an unseen envelope that outweighs all the star's gas and dust combined. The halo of dark matter extends for hundreds of thousands of light years, beyond the visible limits, forming a quiet gravitational field that binds the Milky Way together. Within this unseen domain, each star's motion is subtly guided. The circular paths of objects in the spiral arms depend on the balance between their speed and the gravitational pull from this dark mass. Without it, the galaxy's outer stars would drift away into intergalactic space, their orbits gradually unbound. But instead they remain held by the gentle pervasive attraction of a substance that neither emits nor absorbs light. This invisible structure acts as the skeleton of the galaxy, shaping the formation of stars clusters and even satellite galaxies that orbit within its gravitational reach. The nature of dark matter remains one of the most profound questions in astrophysics. Its particles, if they exist as such, interact so weakly that they pass through ordinary matter almost without trace. Billions flow through every human body each second without effect. They exert gravity but otherwise leave no mark, no glow, no heat. It is a quiet presence detectable only in the aggregate through the collective motion of galaxies and the bending of light from distant objects. In the Milky Way, dark matter accounts for roughly 85% of the total mass, a silent majority shaping every pattern of motion while remaining utterly invisible. The dark halo is not uniform. Computer models and gravitational measurements suggest it is denser near the center, gradually thinning outward. It may contain substructures, small clumps of dark matter that never formed stars but still exert their own pull. These clumps could subtly influence the orbits of stellar streams or the shapes of satellite galaxies. Yet even these disturbances occur slowly over cosmic timescales, so that the overall motion remains smooth. There is no turbulence in the dark matter halo, only the steady curvature of space shaped by mass. The distribution of dark matter also defines how the Milky Way interacts with its environment. The gravitational influence of the halo reaches far beyond the visible disk, affecting nearby dwarf galaxies and shaping the local group, the small family of galaxies that includes Andromeda Triangulum and dozens of smaller systems. Each member moves not through emptiness, but through a shared gravitational landscape formed by overlapping dark halos. The Milky Way's halo and that of Andromeda may already be touching their outer regions, merging quietly as the two galaxies drift toward one another in a slow approach that will take billions of years. Although dark matter cannot be seen, its presence can be traced indirectly through gravitational lensing, a subtle effect where light from distant galaxies is bent by invisible mass. When viewed through powerful telescopes, these distortions reveal how dark matter is distributed, confirming that the Milky Way sits within an enormous, softly rounded envelope. The shape of this halo is roughly spherical, though slightly flattened by the disk's rotation. It extends well beyond the realm of visible stars, reaching perhaps 200,000 or 300,000 light-years in radius. Inside this expanse, the density of dark matter is highest near the center, providing a deep gravitational potential that anchors the galaxy's luminous disk. The quiet stability provided by dark matter allows the Milky Way to maintain its spiral shape over immense timescales. The stars in the disk orbit the center every few 100 million years, yet the overall structure endures, supported by the dark halo's gravity. Without it, the spiral arms would gradually unwind, and the outer gas clouds would disperse. Instead, they remain gently bound, moving in graceful circular paths. The halo ensures that the galaxy's energy is balanced, its rotations smooth, its motions harmonized. In this way, something unseen becomes the source of visible order. Though undetectable directly, the idea of dark matter arose from careful observation. In the mid-20th century, astronomers studying the rotation curves of galaxies noticed that stars far from their centers moved too quickly. Rather than slowing down as predicted by Newtonian gravity applied to visible mass, the velocities remained constant. The simplest explanation was that each galaxy contains a vast reservoir of unseen matter. Over decades, this pattern was confirmed in galaxy after galaxy, including our own. The conclusion became inescapable. The universe is dominated by a component that does not emit light, but shapes its large-scale structure. Within the Milky Way, the dark matter halo interacts gravitationally with all visible components. It guides the paths of satellite galaxies, defines the orbits of globular clusters, and maintains the coherence of the galactic disk. Yet despite this deep influence, it behaves quietly. There are no sudden fluctuations or bursts. The halo's gravity changes only as stars shift within it, but even those motions unfold over billions of years. It is a constant background presence, invisible, pervasive, and stable. The interplay between dark matter and ordinary matter also influenced how the Milky Way formed. In the early universe, dark matter began to clump together first, its gravity attracting gas that later cooled to form stars and galaxies. The luminous components we see today are embedded within the dark framework that emerged long before them. Every spiral galaxy owes its existence to this underlying structure, and the Milky Way is no exception. Its stars and gas occupy a small region near the center of a much larger unseen sphere. The mystery of dark matter remains unresolved. Scientists continue to search for its nature through underground detectors, particle accelerators, and astronomical surveys. Yet no confirmed detection has been made. For now, it remains a theoretical shadow that matches observation perfectly, while eluding every direct test. Its silence is total. It neither glows nor collides, neither absorbs nor reflects. It simply is a quiet gravitational foundation upon which the luminous galaxy rests. If one could stand at the edge of this halo and look inward, the Milky Way's disk would appear suspended in the center, like a glowing whirlpool of light. The halo itself would be invisible, its presence known only through the slow rotation of the stars within. Around it, the faint glimmer of satellite galaxies would drift like sparks in the night. Nothing would move quickly. Every orbit, every interaction would unfold across eons, balanced perfectly between expansion and collapse. It is a realm of stability where gravity acts not as a force of conflict, but as a soft field holding all things in quiet cohesion. Within this enclosure, the Milky Way turns serenely, its visible parts carried effortlessly within an unseen embrace. The stars, the gas, the dust, and even the planets orbit within the calm architecture of something that cannot be seen. This is the galaxy's hidden skeleton, its unbroken frame surrounding it in a still enduring gravity that defines its shape and ensures its peace. Beyond the luminous disk of stars, the Milky Way extends into a diffuse region of gas and dust so faint that its glow can barely be detected. This extended envelope, known as the circumgalactic medium, forms a vast transition between the bright spiral interior and the dark reaches of intergalactic space. It contains immense reservoirs of hydrogen, helium, and trace elements stretched across hundreds of thousands of light years. The material here is almost unimaginably thin, yet because it occupies such enormous volumes, its total mass may rival that of all the stars combined. The gas exists in multiple phases, some cool and clumpy, some hot and ionized, all interwoven in a delicate equilibrium. This region acts as both a boundary and a lifeline, regulating how matter flows into and out of the galaxy. The hot component of this medium forms a halo of X-ray emitting gas that envelops the Milky Way entirely. With temperatures of millions of degrees, it glows faintly in high-energy light invisible to human eyes, but measurable by orbiting observatories. Despite its heat, the gas is extraordinarily thin, with particles separated by many kilometers. The pressure is so low that collisions are rare, Yet over cosmic distances, these rare interactions shape the galaxy's evolution. The hot halo helps recycle material ejected by supernovae and stellar winds, allowing it to cool gradually and eventually fall back toward the disk where new generations of stars will form. In this way, the extended envelope acts as a quiet intermediary between the interstellar medium and the vast cosmic web beyond. Mixed with this hot plasma are cooler filaments of hydrogen gas extending like faint translucent rivers. These filaments, detected through radio observations, reveal where the galaxy continues to gather material from its surroundings. Streams of gas from the Magellanic Clouds and other satellite systems feed the Milky Way's outskirts, drifting inward under gravity. The gas moves at speeds of hundreds of kilometers per second, but its flow is smooth spread across such vast scales that the motion appears slow and continuous. It takes hundreds of millions of years for this material to travel from the halo to the disk. Over time, these inflows replenish the galaxy's reserves of star-forming gas, ensuring that its spiral arms remain active. Embedded within this diffuse medium are also faint traces of dust, tiny solid grains composed of silicates, carbon and metals forged in ancient stars. Although dust accounts for only a small fraction of the halo's mass, its presence softens starlight passing through, scattering blue wavelengths and leaving a subtle reddish tint. The grains are carried outward by stellar winds and supernova explosions, then dispersed through the circumgalactic volume. Some eventually escape into intergalactic space, while others fall back into the disk to participate once more in the cycle of star formation. Each grain endures for millions of years, drifting silently between the stars. The circumgalactic medium also acts as a record of the galaxy's past activity. Chemical traces within it reveal how much material has been expelled by dying stars, how much has been accreted from the cosmic environment, and how both processes balance over time. Observations show that this region is rich in heavy elements, suggesting that the Milky Way has been steadily enriching its surroundings for billions of years. Yet the enrichment is not uniform. Some areas remain nearly pristine, while others carry the fingerprints of countless stellar generations. This patchwork composition reflects the slow-breathing rhythm of the galaxy material, moving outward through winds and supernovae, then falling inward again through cooling and condensation. The interplay between hot and cool gas in this outer envelope is gentle but continuous. Pockets of cooler gas condense where density fluctuations occur, forming clouds that drift inward. These clouds are enormous, often spanning tens of light years, but they remain diffuse with densities lower than any vacuum achievable on Earth. As they move through the halo, they experience drag and gradual heating, sometimes fragmenting before reaching the disk. Yet even in their destruction, they return matter to the galaxy in a slow cascade. The process is cyclical, not violent, a constant exchange between the galaxy and its surroundings that maintains balance across cosmic timescales. For observers studying the Milky Way from within the circumgalactic medium is difficult to perceive directly. Its glow is faint and it emits primarily in wavelengths absorbed by Earth's atmosphere. Only through space-based telescopes has its structure begun to emerge. Instruments aboard the Hubble Space Telescope and X-ray observatories have traced its faint emissions and absorption lines, revealing a vast, nearly spherical cloud enveloping the entire galaxy. Its outer boundary merges gradually into the intergalactic medium, blending the Milky Way into the larger cosmic network. There is no sharp edge, no visible frontier, only a gradual fading of matter into emptiness. Within this region, temperature and density vary smoothly with distance from the galactic center. Near the disk, the gas is cooler and denser, influenced by the activity of stars and supernovae. Farther out, it becomes hotter and thinner, supported by the gravitational field of the dark matter halo. Magnetic fields thread through the gas, faint but coherent, shaping its slow flow. Cosmic rays, high-energy particles accelerated by stellar events, diffuse through the medium, carrying energy and altering its chemistry. Yet despite these processes, the circumgalactic environment remains remarkably stable. Its immense size ensures that changes occur only over billions of years. The envelope of gas and dust serves another purpose. It shields the galaxy from the full impact of the intergalactic environment. The Milky Way moves through space at hundreds of kilometers per second, and the halo acts as a buffer, absorbing and redistributing the weak pressure of the cosmic medium. It softens interactions with incoming material, allowing the galaxy to evolve peacefully within its orbit, around the local group's center of mass. This buffering effect preserves the delicate structures of the disk and spiral arms, ensuring that star formation and rotation continue without disruption. If one could view the Milky Way from a distance, the circumgalactic medium would appear as a vast, faintly glowing sphere surrounding the bright spiral core. The central disk would seem like a concentrated ribbon of light suspended within a misty halo, the whole system drifting silently through space. The glow would be faint, almost imperceptible, the product of scattered starlight and thin gas heated by gravity. It would resemble the faint outline of a breath, a tenuous aura that defines the galaxy's presence in the cosmos. Within it, every photon of light, every atom of gas, and every grain of dust participates in a quiet equilibrium maintained over billions of years. The extended envelope is both the galaxy's frontier and its connection to the universe beyond. It gathers matter from intergalactic filaments, returns enriched material from dying stars, and moderates the constant exchange between inside and outside. Nothing here is static. Everything moves, yet so slowly that from any single vantage point it appears perfectly still. It is the Milky Way's outer breath, vast, calm and steady, maintaining the continuity of matter between the galaxy and the endless dark that surrounds it. At the edge of the Milky Way's bright disk, the orderly plane of stars and gas begins to bend. This subtle curvature, known as the galactic warp, is one of the most graceful features of the galaxy's architecture. Rather than lying flat, the outer disk tilts gently upward on one side and downward on the other, forming a slow wave-like distortion that extends tens of thousands of light-years above and below the central plane. The effect is slight compared to the galaxy's overall diameter, yet over such immense distances, even a small inclination becomes striking. The warp is most visible in the distribution of neutral hydrogen gas, which reaches farther out than the stellar disk. When mapped in radio wavelengths, the gas outlines a pattern that curves smoothly, as though the entire structure were breathing in a shallow motion. The cause of this bending lies in a complex interplay of gravity, motion, and time. The Milky Way is not isolated. It moves through a dynamic cosmic environment influenced by nearby galaxies, streams of dark matter, and its own internal rotation. The most likely source of the warp is the gravitational pull of the Large and Small Magellanic Clouds, the two dwarf galaxies orbiting the Milky Way at great distances. Their combined influence, along with the mass of the dark matter halo, may tug on the outer disk unevenly, causing it to oscillate slowly. These motions unfold over billions of years, too gradual to observe directly, yet they leave a lasting imprint on the galaxy's shape. The warp may also carry traces of past interactions with smaller galaxies, now dissolved into the halo. Each encounter would have sent ripples through the disk, which then persisted as the system slowly returned to equilibrium. Within the warped region, stars and gas still follow their orbits, faithfully circling the galactic center once every few 100 million years. The tilt alters the angle of their paths but not their stability. From within the disk, this warping is imperceptible. Only by stepping far outside could one see the full curvature. To an observer viewing the Milky Way from a distant vantage point, the warp would appear as a gentle twist at the edges of the luminous spiral, a slow undulation that gives the galaxy a living three-dimensional form. The stars near the outermost rim move in harmony with the disk's rotation, tracing arcs that rise and fall in smooth rhythm. The galactic warp also affects how light and matter are distributed. Because the outer disk is tilted, distant regions of gas and dust overlap along the line of sight, creating subtle asymmetries in brightness when the Milky Way is viewed from Earth. The northern and southern halves of the galactic plane do not appear perfectly symmetrical. One side rises slightly higher, glowing faintly above the central band of starlight. Observations by the Gaia mission have confirmed that millions of stars participate in this vast motion, bending collectively under the galaxy's gravitational field. The amplitude of the warp increases with distance from the center, reaching several thousand light-years at the outermost edges, yet the motion remains smooth without sudden distortions or turbulence. The bending of the disk also has gentle effects on the interstellar medium. Gas clouds in the warped regions move through slightly inclined paths, causing variations in density and pressure that influence where new stars form. In places where the disk tilts upward, gas may cool and condense differently than in regions lying flatter. Over time, these variations create subtle patterns in the distribution of star-forming regions and dust lanes. The result is not chaos but diversity, a quiet asymmetry that adds texture to the Milky Way's structure. The warp ensures that the galaxy is not a perfect rigid disk, but a dynamic, flexible system responding to its surroundings. Some models suggest that the warp oscillates, slowly shifting its orientation over cosmic time. If so, the outer disk may rise and fall like a great slow wave moving through the sea of stars. These oscillations could be driven by changes in the gravitational field of the dark matter halo or by the passage of satellite galaxies. Yet the timescales involved are so long that even the most precise measurements reveal only hints of motion. From any human perspective, the warp is effectively frozen its shape constant across the entire span of recorded observation. This apparent stillness reinforces the galaxy's sense of calm, a structure in motion so vast that its dynamics appear motionless. Beyond the warped edges, the density of stars drops sharply. Here the Milky Way begins to merge with the extended gas envelope that surrounds it. The warp may help channel some of that gas inward guiding material from the circumgalactic medium into the outer spiral arms. As this gas settles into the disk, it replenishes the galaxy's supply of star-forming material. In this way, the warp serves both as a structural feature and a gateway between the galaxy's interior and its surroundings. The process is gentle and continuous, maintaining the slow equilibrium between inflow and rotation. The shape of the warp has been mapped most clearly in radiolight, which can penetrate the dust that obscures optical views. Radio telescopes across Earth have traced the pattern of neutral hydrogen gas, revealing the bending of the disk on both sides of the galactic plane. The data show that the warp is asymmetric, with one side slightly higher and more extended than the other. This imbalance hints at the uneven gravitational influences acting upon the Milky Way, perhaps from the Magellanic Clouds, or from irregularities in the dark matter halo itself. Despite these asymmetries, the overall structure remains balanced. The disk continues to rotate smoothly, its motion unaffected by the slow bending of its form. If one could view the Milky Way in full, the warp would lend it a subtle elegance. The central bulge would glow warmly, surrounded by sweeping arms that curve outward and then lift gently toward their ends. The edges would appear to ripple softly as though the galaxy were suspended in a calm breeze. This is not a violent distortion, but a quiet expression of balance, the outer regions responding delicately to the gravitational landscape in which they float. In the vast silence of space where the timescale of motion stretches beyond imagination, even such a vast deformation is serene. The warp reminds astronomers that the Milky Way is not a static picture but a living system. Its shape evolves, slowly moulded by gravity inertia and the faint influence of neighbouring galaxies. Yet this evolution occurs so gradually that for millions of generations the galaxy appears unchanged. The warp's gentle curve is a sign not of instability but of endurance, a steady adaptation to external forces over cosmic time. The Milky Way bends, but it does not break. It yields slightly to the pull of its companions while maintaining the quiet rotation that defines its structure. At the farthest edges of the disk, stars rise and fall in their paths, tracing graceful arcs above and below the plane. Each motion contributes to the overall pattern, a collective choreography, guided by gravity and preserved by time. There are no sudden jolts, no sharp boundaries, only gradual transitions between regions of light and shadow, density and emptiness. The warped outer disk is the Milky Way's slowest movement, a subtle tilt, a quiet wave, a sign of its continued balance within the cosmic sea that surrounds it. Moving inward from the warped edges, the Milky Way's structure begins to take on a familiar and graceful order. Here at the outer fringes of the spiral arms, the faint glow of starlight gathers into gentle curves that wind slowly around the galactic centre. The arms are not solid structures, but rather regions where stars and gas are more densely concentrated, shaped by the combined effects of gravity orbital motion and waves of star formation. In the outskirts, these patterns emerge subtly. The stars are spaced far apart, the gas clouds diffuse, and the spiral pattern appears as a soft increase in brightness rather than a sharp feature. This is the realm where the ordered rotation of the galaxy meets the quiet emptiness of the halo, a threshold between structure and openness. The arms here are broad and low, in contrast defined more by their rhythm than their boundaries. The outer spiral arms move with the galaxy's rotation, but not as rigid lines. Instead, they act as long, slow-moving waves, each section rotating at a slightly different speed. The stars within them drift through, born within the arm's denser regions, and then moving outward as their orbits carry them ahead. What gives the Milky Way its spiral shape is not the fixed placement of matter, but the steady propagation of these waves regions of higher density that move through the disk like ripples across water. In the outermost regions, these ripples weaken their amplitude, decreasing with distance from the centre. Yet they persist, maintaining the quiet coherence of the spiral form even in areas where star formation has nearly ceased. Most of the gas here is atomic hydrogen, detectable only through its faint radio emission. In visible light, these areas appear dark and sparse, yet radio telescopes reveal the continuing pattern, vast arcs of gas extending far beyond the regions where stars dominate. This hydrogen forms the raw material from which new generations of stars could one day arise. At present, the outer arms are mostly calm. Star formation occurs only occasionally, triggered by gentle compressions as gas clouds move through the slow waves of density. These isolated regions of activity produce clusters of young blue stars that shine briefly before fading into the background population. Over time, their light adds to the faint glow that traces the spiral from afar. Dust is also present in these outskirts, though it is spread thinly through the gas. The grains absorb and scatter light from stars deeper within the disk, producing subtle, reddening effects that can only be seen in long exposures. The dust follows the same spiral pattern as the gas aligned along lanes that mark the faint outlines of the arms. Occasionally, denser knots of dust appear, relics of molecular clouds where star formation once occurred. These remnants drift slowly outward, dispersing over millions of years until they are indistinguishable from the surrounding medium. The entire outer disk is thus a place of fading motion, a quiet region where the traces of past activity remain visible, even as new processes move at an almost imperceptible pace. As one looks closer toward the center, the arms become more defined. The spiral pattern tightens slightly, and the distribution of stars becomes smoother. The outer arms, often referred to as the outer and Perseus arms, form the largest and most extended features of this region. They curve gracefully around the galaxy, each spanning hundreds of thousands of light years. Between them lie vast interarm spaces, where the density of stars drops, creating wide corridors of relative emptiness. Yet even in these gaps, faint streams of gas and small groups of stars persist, ensuring continuity across the disk. The arms do not begin or end abruptly, but fade gradually, their boundaries blending with the background of older stars. The rotation of the outer disk is slow but stable. Each star completes a single orbit around the galactic center in roughly 250 million years, meaning the galaxy has turned only a few dozen times since its formation. Because the outer regions move more slowly than those near the center, the spiral pattern continually adjusts, stretching and reshaping over time. Yet gravitational resonances and the self-organizing nature of the density waves maintain the overall form. This equilibrium creates a sense of calm structure, a slow rhythm that persists across billions of years. The spiral arms are not frozen. They are alive with gradual change, but the pace is so measured that the entire system appears timeless. The outer arms also play a role in moderating the flow of gas within the galaxy. As material from the halo and circumgalactic medium falls inward, it encounters the spiral pattern and becomes organized along its ridges. The gas slows, cools, and begins to settle into the rotating disk. Some of it eventually drifts further inward to fuel star formation in the inner arms. This process acts like a quiet current guiding material toward the heart of the galaxy. The arms thus serve as pathways, not channels of turbulence, but smooth, regulated conduits through which matter circulates over immense timescales. Viewed from above, the Milky Way's spiral structure would appear faint and diffuse in the outer regions, becoming brighter toward the middle. The arms would trace pale, luminous arcs across a background of dark interstellar space. Their shapes would seem fixed, yet if one could watch for millions of years, the patterns would slowly twist, unwind, and reform, creating a living geometry of motion. Each arm contains stars of every age, from newborns in glowing nebulae to ancient suns nearing the end of their lives. Together they form the dynamic architecture of the galaxy, an elegant balance of change and continuity. The outer arms are also home to many of the Milky Way's most subtle patterns of motion. Small oscillations in the rotation curve, gentle deviations in velocity, and faint ripples in density all hint at the complex gravitational interactions shaping the disk. These features may result from the galaxy's encounters with satellite systems, or from the uneven distribution of dark matter beneath the disk. Yet none of these influences disrupts the overall harmony. The arms continue their slow rotation, each feature blending seamlessly into the next. The motions of hundreds of billions of stars combine into a single coherent flow, a cosmic choreography so vast that it appears utterly still. From the perspective of Earth, much of the spiral pattern is hidden by dust and distance. The Milky Way's edge-on orientation makes it difficult to trace the arms directly, but measurements of gas dust and star velocities allow astronomers to reconstruct their shape. The result is a map not of individual stars but of large-scale patterns, soft gradients of density forming spirals that connect the entire galaxy. In radio light, the arms appear as luminous filaments against the darkness, their positions and thickness revealing the slow rotation of the disk. The farther one looks, the more the structure fades until at last the spiral dissolves into the faint haze of the halo. The outskirts of the spiral arms represent a balance between order and dissolution. Here the forces that shape the galaxy reach their limit, giving way to the quiet of intergalactic space. Yet even in this boundary zone, the spiral pattern endures its gentle curvature preserved by gravity and motion. It is a region of quiet persistence where the Milky Way maintains its form with effortless grace. Each star, each cloud, each grain of dust contributes to a collective pattern that has endured for billions of years, a pattern that moves so slowly and so smoothly that to any watcher within it the galaxy seems at rest. Deeper within the disk, the Milky Way's spiral pattern reveals its full grace. The main arms, known as Perseus and Scutum Centaurus, sweep outward from the central regions in vast glowing curves that span hundreds of thousands of light years. These arms define the galaxy's structure, organizing its stars, gas and dust into a coherent, slowly rotating pattern. Each arm is a mixture of generations' newborn stars in bright nebulae, mature suns tracing the galaxy's path, and ancient redder stars that drift quietly between them. The spiral pattern is not solid but fluid, a density wave moving through the disk, compressing gas and dust as it passes sparking star formation and leaving a trail of fading starlight behind. It is a process both dynamic and tranquil, its rhythm measured not in years but in hundreds of millions of years. The arms themselves rotate at a steady rate while the stars within them move slightly faster or slower, creating a continuous flow that gives the illusion of permanence. Each arm follows the gravitational influence of the galaxy's mass distribution. Where the density of matter increases, gas clouds slow and accumulate, forming long lanes of interstellar dust that mark the arm's inner edges. Within these lanes, the pressure rises just enough to trigger the collapse of molecular clouds. In these cold, dense regions, stars are born in groups, their light illuminating the surrounding dust into glowing emission nebulae. Over millions of years, the young stars drift away, leaving behind the diffuse glow of older populations. This constant renewal maintains the arm's structure, ensuring that they remain visible even as individual stars move in and out of them. The process is self-sustaining, a quiet interplay of gravity and motion that keeps the spiral pattern alive. The Perseus arm, one of the Milky Way's major features, lies beyond the solar system's orbit, curving gracefully through the outer disk. It contains some of the galaxy's brightest star-forming regions, including immense nebulae, where clusters of hot young stars illuminate clouds of hydrogen gas. These nebulae, visible in radio and infrared light, form intricate filaments shaped by stellar winds and supernova remnants. Yet despite their energy, the overall scene remains calm when viewed on a galactic scale. Each burst of star formation contributes only a small fraction to the arm's luminosity, and the structure as a whole evolves with quiet continuity. Closer to the galactic center lies the Scutum Centaurus arm, the other dominant spiral feature. It is thicker, denser, and more luminous, extending inward toward the bar that crosses the center. This arm contains vast reservoirs of molecular gas, the raw material of future stars. Embedded within it are regions where gravity and pressure combine to ignite thousands of suns, each cluster adding to the soft glow that defines the arm. Observations in infrared light reveal long filaments of dust, tracing the arm's curvature their dark outlines silhouetted against the diffuse background of starlight. The light absorbed by these dust lanes is re-emitted as a faint infrared warmth, allowing astronomers to map the arms even where visible light cannot reach. Between these two major structures lie minor arms and spurs such as the Sagittarius arm and the Norma arm, which act as bridges between the main spirals. They too host clusters, clouds, and regions of quiet starbirth. Together, these arms form a graceful interconnected network that winds around the galaxy 4 times before fading into the outer disk. The pattern is not perfectly symmetrical. Each arm differs slightly in thickness, brightness, and extent. Yet these differences add depth and variation, giving the Milky Way its natural organic form. The spiral is not the product of rigid geometry, but of a balance between order and randomness held steady by gravity's quiet persistence. The arms also serve as the galaxy's circulatory system. Gas and dust flow through them, slowly compressed by the passing density waves, and then expanding again as they move onward. This cyclical motion keeps the interstellar medium in gentle motion, preventing stagnation. Over time, heavy elements produced by stars are mixed throughout the disk, enriching the material from which new stars form. The process unfolds with elegant regularity, maintaining the galaxy's long-term balance. On timescales of billions of years, the arms drift and change, yet the overall spiral form endures. It is a self-perpetuating pattern, continually refreshed by the very stars it creates. For observers on Earth, the spiral arms reveal themselves as the glowing band of the Milky Way that stretches across the night sky. What appears as a continuous ribbon of light is in truth the combined glow of countless stars within the disk, seen edge-on from within. Dust obscures much of the view, but through infrared and radio observations, astronomers can trace the arms' positions and movements. The Gaia mission, mapping over 1 billion stars, has revealed their subtle motions in exquisite detail. The data show not chaos, but harmony stars moving in smooth, predictable orbits guided by gravity and the invisible structure of the spiral pattern. The stability of these arms is sustained by the galaxy's dark matter halo, whose mass provides the gravitational foundation needed to keep the outer disk rotating smoothly. Without this hidden support, the spiral would unravel over time. Instead, the Milky Way maintains its shape through a delicate equilibrium, the inward pull of gravity balanced by the outward motion of rotation. Within this balance, the spiral arms act as visible markers of the galaxy's ongoing evolution, tracing the pathways of matter as it moves through the disk. The major arms also define the rhythm of the galaxy's chemical life. Each generation of stars forms, shines, and eventually dies, returning elements to the interstellar medium. Supernovae and stellar winds disperse these elements, seeding nearby clouds with the materials for new planets and stars. The process is continuous yet gentle in its overall effect. The arms breathe, expanding slightly as gas accumulates, contracting as stars form and consume it, but their motion is slow and steady. Over billions of years, this quiet breathing sustains the Milky Way's luminous spiral without disruption. If one could watch the galaxy from above, the major arms would appear as luminous rivers winding outward from the bright central bulge. They would move imperceptibly, their shape slowly changing but never losing its harmony. Within them, countless stars would shine and fade their collective light, forming a constant soft glow that defines the Milky Way's face. The scene would not suggest chaos or violence, but enduring order, a quiet demonstration of balance on a cosmic scale. The spiral arms are both the galaxy's framework and its living pulse, immense, serene, and endlessly turning through the dark. Between the Milky Way's sweeping spiral arms lie wide stretches of space that seem at first glance almost empty. These interarm regions occupy much of the disk's volume, extending for thousands of light-years between the luminous arcs of the spiral pattern. They form the galaxy's quieter corridors where star formation slows gas densities drop and the pace of change becomes even more gradual. Yet these areas are not voids. They contain a vast population of older stars, thin streams of gas and faint clouds of dust, the remnants and travelers of previous generations that have drifted out of the denser arms. The light here is soft and diffuse, a gentle background glow produced by countless stars too faint to stand out individually. When viewed in aggregate, they create a steady luminosity that fills the spaces between the arms with a calm, unbroken radiance. The stars in these regions move in the same broad rotation as the rest of the disk, but their distribution is smoother, less clumped into clusters. Most are middle-aged or old, having formed long ago within the spiral arms before their orbits carried them onward. As a result, the interarm regions act as repositories of the galaxy's stellar history, containing suns that trace back to epochs when the Milky Way's spiral structure looked slightly different from today. Their motions are stable and predictable, guided by the galaxy's gravitational field. Though each follows its own orbit together, they form a vast, orderly flow, a stellar river encircling the galactic center in a slow, graceful procession. The interstellar gas found here is diffuse, spread too thin to collapse easily into new stars. Its pressure and temperature vary gently, forming an equilibrium that can persist for millions of years. Occasional density fluctuations triggered by the passage of spiral density waves or by shock fronts from distant supernovae may briefly compress the gas, but most of these disturbances fade before igniting star formation. The result is a tranquil environment dominated by soft radiation from surrounding stars and faint emissions from rarefied hydrogen. In visible light, such regions appear dark compared to the bright arms, but in radio and infrared wavelengths, they reveal subtle threads of gas and dust that tie the spiral pattern together. These regions are also vital for the long-term stability of the galaxy. As stars and gas move out of the spiral arms, they enter the interarm zones and gradually mix with material from other parts of the disk. This process redistributes angular momentum and chemical elements, preventing sharp contrasts that could destabilize the structure. The interarm spaces act as a buffer between areas of active star formation, allowing the galaxy's overall rotation to remain smooth and uniform. Without them, the spiral pattern might become turbulent or chaotic. Instead, it remains balanced with alternating regions of activity and calm, forming a continuous rhythm across the disk. For astronomers observing from within the Milky Way, the interarm regions are difficult to define precisely. Because the Sun lies in one of these quieter areas, the Orion Spur, a small offshoot between two major arms, our perspective emphasizes their importance. Much of the night sky's starlight comes from interarm populations, ordinary suns, unremarkable in brightness, but abundant in number. Their collective glow forms the faint background against which brighter clusters and nebulae appear. Through infrared surveys, astronomers have mapped how these stars trace the galaxy's gravitational potential, showing that the interarm regions are as essential to the Milky Way's stability as the arms themselves. Dust is also present here, though more thinly spread. Its grains absorb and scatter light, giving the Milky Way's band its mottled appearance when viewed from Earth. These dust particles are remnants of earlier star-forming cycles ejected from dying stars and carried outward by radiation pressure and stellar winds. Over time, they drift between the arms, cooling the interstellar gas and serving as catalysts for chemical reactions that form molecules. Even in these quiet zones, dust plays a subtle but continuous role in shaping the galaxy's ecology. It absorbs energetic photons, re-emits them as gentle infrared warmth, and ensures that the interarm medium remains in thermal balance. Within the calm of the interarm regions, isolated molecular clouds sometimes persist remnants of gas drawn outward from the spiral arms. These clouds are small compared to the great star-forming complexes deeper within the arms, yet they maintain structure for long periods. Occasionally, gravitational interactions or collisions with passing density waves may compress them enough to trigger modest bursts of star formation. Such events produce small associations of young stars, often short-lived and quickly dispersed. They do not disrupt the tranquility of the interarm environment, but instead add brief points of renewal before fading into the background. The stellar populations here exhibit a wide range of ages and compositions. Older metal-poor stars coexist with younger metal-rich ones, their orbits intersecting as they drift through the disk. Over billions of years, this slow mixing smooths out gradients in metallicity, ensuring that the Milky Way's chemical evolution proceeds uniformly. This process happens without turbulence or shocks, a quiet diffusion across immense distances. The interarm regions thus act as a long-term integrator, blending the results of many cycles of stellar birth and death into a single balanced whole. Light travels easily through these regions. Because the density of dust and gas is lower, starlight can pass across thousands of light years with minimal scattering. From Earth's perspective, this transparency allows astronomers to peer deep into the galaxy, observing objects far beyond our immediate surroundings. The interarm gaps become windows through which the inner structure of the Milky Way can be glimpsed. They are not empty voids, but transparent corridors providing clarity where the arms themselves are opaque with dust. In this sense, the calm of these spaces has both physical and observational significance. It reveals what lies deeper within. The gravitational field in the interarm regions is dominated by the combined influence of the disk and the dark matter halo. Together they ensure that stellar motions remain smooth and nearly circular. Small oscillations known as epicyclic motions cause stars to drift slightly inward and outward as they orbit, creating gentle waves of density that move through the disk. These oscillations are faint echoes of the spiral density waves rippling through the interarm zones and maintaining the galaxy's overall coherence. Over time, such oscillations fade, leaving only the quiet rotation of the disk. If the Milky Way could be viewed from far above, the interarm regions would appear as the soft spaces between the glowing arms, filled with diffuse light that smooths the contrast between bright and dark. They would form a subtle grey-blue mist encircling the galaxy, their calm luminosity balancing the vibrancy of the spiral pattern. Within them the stars would drift like dust in sunlight, unhurried and unchanging. Their motions, though individually random, would merge into a single flowing continuity, the great rotation of the galaxy maintained by gravity and time. In these wide, silent stretches between the arms, the Milky Way reveals its endurance. Here there is no rush of star birth, no bright nebulae or dense clusters, only the quiet persistence of stars that have outlasted the cycles of creation and destruction. They move endlessly, carrying with them the memory of the arms from which they came, and awaiting the next passage of a spiral wave that may someday gather them again. The interarm regions are the galaxy's intervals of rest, the spaces between breaths in its slow, eternal rhythm. The Orion Spur is a small, unassuming branch of the Milky Way's grand spiral, yet it is here within this modest corridor of stars that the solar system resides. Stretching for only a few thousand light-years, the spur lies between two of the galaxy's major arms, the Sagittarius arm toward the galactic center, and the Perseus arm toward the outer disk. It is not a dominant structure, but a local bridge, a transitional lane where gas dust and stars gather in a loosely organized pattern. The Orion spur is a minor feature in the Milky Way's architecture, yet from within it the entire galaxy unfolds around us. To observers on Earth, the Milky Way's luminous band across the night sky is shaped largely by our position in this quiet spur where the balance between density and openness provides a clear, stable window onto the surrounding spiral arms. The spur's structure is defined by gentle curves of gas and dust, interspersed with small clusters of young stars. It has no sharp boundaries merging gradually into the larger arms on either side. The gas within it forms long filaments and diffuse clouds, many of which are sites of mild star formation. These regions glow faintly in hydrogen emission, marking the slow transformation of gas into new stars. Unlike the crowded interiors of the major arms where starbirth occurs in massive clusters, the Orion spur's activity is modest. The balance of conditions, neither too dense nor too diffuse, allows it to remain stable for long periods. This stability makes it an ideal region for planetary systems like our own to evolve in relative calm. Within the spur lie several familiar stellar landmarks. The Orion Nebula, visible to the naked eye as a faint patch in the constellation, Orion is one of the brightest star-forming regions in the entire Milky Way. It is part of a vast molecular complex spanning hundreds of light years, where new stars emerge from dense clouds of gas and dust. Nearby lie the Pleiades and Hyades clusters in Taurus, both young groups of stars that illuminate the surrounding interstellar medium. Other notable features include the Cygnus X complex, Carina's bright nebulae, and the Vela region, all linked loosely by the Orion spur's extended structure. Together they form a chain of quiet brilliance, a series of small luminous oases in a wider landscape of darkness and dust. The spur is also home to the local bubble, a cavity of low-density gas that surrounds the Sun and several nearby stars. This bubble, thought to have formed from ancient supernovae, extends for hundreds of light years and provides a relatively clear view through the interstellar medium. Within it, the gas density is far lower than average, and magnetic fields are weak and diffuse. This clarity allows light from distant regions of the Milky Way to reach us more easily, contributing to the galaxy's visibility in our sky. The local bubble connects to adjacent cavities through narrow tunnels of low-density gas, forming a network of interstellar voids that thread the Orion spur. These voids are peaceful and stable, maintained by the slow balance of stellar winds and supernova remnants that sculpt the surrounding material. The stars of the Orion spur range widely in age and composition. Some are young, massive, and short-lived, shining blue and white with intense luminosity. Others are middle-aged, like the Sun, stable and steady for billions of years. Many are old red giants nearing the end of their lives, slowly shedding outer layers that enrich the interstellar medium. This diversity of ages reflects the spur's transitional role within the galaxy. It gathers material from nearby arms, converts some into new stars, and gradually disperses older ones into the surrounding disk. The overall effect is gentle continuity, a region in which the processes of creation and dispersal are balanced in near-perfect harmony. The Orion spur's position also influences our perception of the Milky Way's scale. From within it, the galaxy's central regions appear as a bright, dense band arcing across the sky, while the outer disk fades into softer light. Because we lie between arms, the dust is less concentrated, allowing clearer lines of sight through the disk. When viewed under dark skies, the Milky Way's structure can be traced as a mosaic of brighter and dimmer patches, the signature of our position in this interarm spur. Each glow, each dark lane, corresponds to clouds and clusters lying along our spiral path. What seems to the naked eye like a continuous river of light is in reality a layered cross-section through the spur's delicate geometry. The Gaia mission's measurements have mapped this region with remarkable precision, revealing the fine details of its structure. The spur is not a simple linear feature, but a branching system of filaments, clusters, and cavities, extending across thousands of light years. Some sections bend gently, suggesting that the spur may be slightly warped by gravitational influences from the surrounding arms. The stars within it move together through space, sharing a broad velocity pattern that reflects their shared orbital path around the galactic center. This collective motion maintains the spur's coherence, preventing it from dispersing, even as it drifts slowly within the disk. The interstellar medium here is dynamic yet calm. Shock waves from distant supernovae ripple through the gas, compressing it in places and rarefying it in others, but these effects are mild compared to the energetic environments of the inner galaxy. The Orion spur's gas clouds cool, slowly emitting faint radiation that can be detected in radio and far-infrared wavelengths. Over millions of years, gravity causes some regions to condense, forming new molecular clouds. Others disperse their gas recycled into the larger galactic circulation. This balance of compression and expansion creates an atmosphere of quiet motion, constant change without chaos. The solar system's location within the spur is especially favorable for long-term stability. It lies roughly halfway between the galactic center and the edge, in a region where tidal forces are mild and stellar densities are moderate. This distance protects the Sun from the gravitational disturbances that are more common closer to the core, while still providing access to the rich mix of heavy elements produced by earlier generations of stars. The result is an environment conducive to planetary formation and eventually to life. The Orion spur may be an unremarkable structure in galactic terms, but its quiet conditions have made it a cradle of habitability for countless worlds like ours. Viewed from afar, the Orion spur would appear as a faint, narrow thread of light running between two great arms of the Milky Way. It would not dominate the galaxy's appearance, but would add subtle depth to its spiral form, a minor but beautiful feature connecting larger structures. Within it, stars drift in their orbits, gas flows gently along gravitational gradients, and dust clouds shimmer in scattered starlight. Everything moves, but nothing hurries. The spur endures as a quiet lane within a vast cosmic city, modest yet vital, bridging the grand architecture of the Milky Way with the intimate neighborhood of the Sun. Here in this calm section of the galaxy, space feels spacious and unthreatening. The slow rotation of the disk continues, carrying the spur along in its steady orbit. Every star, from the faintest red dwarf to the most luminous blue giant, contributes to the soft collective glow that fills this region. The Orion spur may not be among the galaxy's great structures, but it is a place of balance, a gentle crossing point in the spiral flow where stars live, light travels, and time unfolds in silence. Within the Orion spur, the region surrounding the Sun forms a small tranquil domain known as the local stellar neighborhood. It spans a few dozen light years in every direction and contains only a handful of stars visible to the unaided eye. Yet within its boundaries, the calm rhythm of the galaxy can be clearly felt. The Sun, together with its planets, drifts slowly through this community of stars, each one following its own orbit around the galactic center. The neighborhood moves as part of the Milky Way's great rotation, traveling at hundreds of kilometers per second relative to the center, but changing position only imperceptibly across human timescales. It is a zone of quiet order where space is vast, the density of matter is low, and gravitational interactions unfold gently over immense intervals of time. The nearest stars lie only a few light years away, but even this distance represents a gulf so great that light takes years to cross it. Between the stars stretches the interstellar medium thin clouds of gas, mostly hydrogen mixed with traces of dust. Within the local bubble, this gas is sparse and warm, providing a clear line of sight through space. The Sun's magnetic field carves a small cavity within it, the heliosphere, where charged particles from the solar wind interact with the surrounding medium. Beyond this boundary, the galaxy resumes its quiet dominance, filling space with faint radiation and cosmic rays that have travelled from distant stars and supernova remnants. The environment is stable, shaped by the balance between stellar winds, magnetic fields, and gravity. The stellar population here is diverse. Proxima Centauri, the closest star to the Sun, is a dim red dwarf, small, cool, and long-lived. Nearby, Alpha Centauri A and B form a binary pair that shines more brightly, their combined light easily visible from Earth's southern hemisphere. Barnard's star Wolf 359, Sirius Epsilon Eridani, and Tau Ceti are among the best-known members of this neighbourhood, each with its own planetary companions and subtle differences in colour and brightness. Most of the stars nearby are red dwarfs, the most common type in the galaxy. They emit faint light invisible to the naked eye, but they dominate by number, forming the quiet backbone of the Milky Way's stellar population. The brighter stars such as Sirius or Vega stand out only because of their proximity or intrinsic luminosity. Together they form a calm, balanced network of suns, each moving through space in harmony with the galaxy's rotation. The motions of these stars create a pattern known as the local standard of rest, a smooth average motion representing the way stars orbit the galactic center near the Sun's radius. Against this reference, the Sun itself drifts gently, moving slightly faster than the surrounding average, completing one full orbit in about 220 million years. The stars nearby follow slightly different paths, their velocities varying by only a few kilometers per second. Over millions of years, their relative positions change slowly, forming a quiet stellar dance in which pairs approach and recede without collision. The vast distances between them ensure peace. Each system evolves in isolation, undisturbed by its neighbours. Within this neighbourhood, open clusters occasionally pass through remnants of star-forming regions born elsewhere in the disk. Over time, gravitational tides from the galaxy disperse these clusters, scattering their members into the general population. The Sun itself likely originated from such a cluster nearly 5 billion years ago. Now dispersed, the other stars born alongside it have moved on, spread thinly through the galactic disk. Occasionally, astronomers identify possible siblings of the Sun by matching their chemical compositions, but these connections are faint, separated by thousands of light years and millions of years of drift. This slow dispersal illustrates how calm yet persistent galactic motion reshapes stellar populations without disrupting their overall stability. The interstellar medium within the local region is patchy, composed of warm, diffuse gas interspersed with colder, denser clouds. Some of these clouds, such as the local interstellar cloud through which the solar system currently moves, are only a few dozen light-years across. They consist primarily of atomic hydrogen, with traces of helium, carbon, and oxygen. Their densities are so low that even the best vacuum chambers on Earth cannot compare. Yet these clouds define the background conditions of space, influencing how light from distant stars reaches us. They absorb certain wavelengths, leaving faint spectral fingerprints that reveal their composition and temperature. Over time, the solar system drifts from one cloud to another, each passage lasting millions of years but causing no disturbance. It is a quiet voyage through a nearly perfect equilibrium. The magnetic fields of nearby stars interact gently with these clouds, shaping the flow of charged particles. The boundaries between stellar winds and interstellar gas are soft and variable, forming bubble-like structures that merge and overlap. The local bubble within which the Sun resides is one of many such cavities. It connects to other voids through narrow tunnels where the gas density drops even further. These interlinked volumes give the galactic disk a porous quality, a three-dimensional texture of light and shadow. In these spaces, supernovae long past have carved low-density corridors through the gas, yet the violence of their origins has long since faded into calm. What remains is a landscape of faint radiation, gently glowing plasma, and fields of dust grains drifting slowly in silence. Astronomers studying the local region use precise measurements from the Gaia mission to map its structure in 3 dimensions. The data reveal not a flat sheet of stars, but a subtle undulation, the disk's warp, extending even into our immediate surroundings. Within a few hundred light years, the stars trace slight vertical motions oscillating above and below the galactic plane. These oscillations occur on timescales of tens of millions of years, too slow to notice, but vital to understanding how the galaxy maintains its balance. They demonstrate that even the calmest areas participate in the grand motion that shapes the Milky Way. The light from nearby stars forms the familiar constellations that have guided human observation for millennia. Yet behind these bright points lies a far richer population of faint suns too dim to be seen without instruments, but filling space evenly in every direction. The neighborhood's average stellar density is about 1 star every few cubic parsecs, vast emptiness, punctuated by rare islands of light. Between them float comets, rogue planets, and clouds of interstellar dust, all moving in quiet harmony with the stars. The calmness of this region is part of what allows planetary systems to remain stable for billions of years. The distances between stars are so great that close encounters are exceedingly rare, ensuring that the gravitational architecture of each system remains undisturbed. If one could look outward from a vantage point within this neighborhood, the Sun would appear as a modest yellow star unremarkable among its peers. Its light would blend with that of thousands of others, each shining steadily in the darkness. The scene would convey not isolation but equilibrium, a cosmic neighborhood of balanced distances and shared motion united by the galaxy's slow rotation. Every star here contributes to the Milky Way's quiet rhythm, turning together around the center in perfect unhurried synchrony. Within this gentle movement, the local stellar neighborhood embodies the galaxy's calmest expression, stability maintained through distance harmony, through motion and silence, through time. Amid the calm rotation of the Milky Way's disk, immense clouds of gas and dust mark the galaxy's creative zones, the regions where stars are born. These star-forming clouds, or giant molecular clouds, are the densest structures in the interstellar medium. They span tens or even hundreds of light years, holding enough material to form thousands of stars. Despite their scale, they are faint and cool, glowing only weakly in infrared light. Seen in visible wavelengths, they appear as dark silhouettes, their dense dust blocking the background glow of the Milky Way. Inside, pressure, temperature, and gravity exist in delicate balance, creating an environment of slow transformation where new suns take shape over millions of years. Within these vast clouds, the galaxy renews itself quietly, turning diffuse gas into luminous stars that will someday illuminate the spiral arms. The gas in these clouds is mostly molecular hydrogen, accompanied by traces of carbon monoxide, water vapor, ammonia, and dust grains, composed of silicates and carbon compounds. The temperature inside is only a few tens of degrees above absolute zero cold, enough for atoms to bind into molecules and for dust to act as a protective shield against starlight. These low temperatures allow gravity to dominate drawing matter, together into knots of increasing density. Yet the process is far from violent. The collapse of a molecular cloud into stars occurs slowly, resisted by internal turbulence, magnetic fields, and rotation. Over time, regions within the cloud become unstable, forming dense cores that begin to contract under their own weight. As they collapse, they warm and brighten, eventually becoming protostars, the earliest stage of stellar life. Across the Milky Way, thousands of such clouds lie along the spiral arms, their presence revealed through radio observations. Among the most famous are the Orion Molecular Cloud Complex, the Carina Nebula, the Eagle Nebula, and the Rosette Nebula. Each is a region of gentle activity on a cosmic scale, where gravity and radiation interact to create intricate structures. The Orion Cloud, lying only about 1,000 light-years away, is one of the closest and best-studied examples. Within it, the Orion Nebula shines as a pocket of active star formation, surrounded by cold, dark filaments where future stars still sleep. In infrared images, these filaments appear as glowing threads of gas lit by embedded young stars. The entire cloud complex stretches for hundreds of light-years, filled with slow-moving currents of material drifting toward its denser regions. Inside these clouds, new stars form in clusters rather than in isolation. Each dense region fragments into many smaller cores, each giving birth to one or more stars. These newborn stars remain hidden for much of their early lives, their light absorbed by surrounding dust. As they grow, radiation and stellar winds begin to clear the surrounding material, carving out cavities that reveal bright nebulae. The balance between creation and dispersal continues for millions of years, gradually transforming the cloud. By the time the young stars emerge, the dense gas that gave birth to them has often been dispersed into space, recycled into the diffuse interstellar medium. Thus, each cloud has a limited lifespan as a stellar nursery, surviving only until the energy of its own offspring breaks it apart. The process of star formation within these clouds is regulated by feedback, the gentle push and pull between gravity drawing matter inward and radiation driving it outward. Massive stars, once formed, emit powerful ultraviolet light that ionizes surrounding hydrogen, producing glowing H2 regions. The edges of these regions expand slowly, compressing nearby gas and sometimes triggering new rounds of star formation. In this way, the life cycle of one generation influences the next, creating a chain of gradual renewal. The overall pace is slow. While individual stars ignite in a few million years, the clouds themselves may persist for tens of millions before dispersing completely. Over time, they drift through the galaxy, shaped by the spiral arms, gravitational waves, and the tidal forces of the disk. Dust plays an essential role within these clouds. The tiny solid particles absorb starlight, cool the gas, and provide surfaces where molecules can form. Without dust, the gas would remain too warm for collapse. Each grain drifts through space for millions of years, gathering layers of ice and organic material before being incorporated into a new star or planet. The same dust that obscures the light of newborn stars also preserves the chemistry that makes planetary systems possible. In this way, even the darkest regions of the galaxy contribute to its luminosity, indirectly nurturing the seeds of future light. The star-forming clouds are not evenly distributed across the Milky Way. They cluster along the spiral arms, tracing the locations where density waves compress gas. The inner regions of the galaxy, where the gravitational field is stronger, tend to host larger and more active complexes, while the outer arms contain smaller and quieter ones. Despite these variations, the fundamental process remains the same. Everywhere, gas cools, condenses, and collapses into stars, returning light to the disk. The calm persistence of this cycle ensures that the Milky Way maintains its glow across cosmic time. From Earth, many of these clouds can be seen as dark patches cutting across the bright band of the Milky Way. The Great Rift, stretching through the constellations Cygnus and Aquila, is a long chain of such clouds, their dust obscuring the starlight behind them. When viewed in the infrared, this darkness transforms into brilliance, a hidden world of warm gas and glowing young stars invisible to the human eye. This duality, dark and luminous, defines the nature of the galaxy's star-forming regions. They are both the shadows and the sources of the Milky Way's light. The birth of stars within these clouds connects every scale of galactic structure, from the diffuse gas of the halo to the bright clusters of the spiral arms. All matter eventually cycles through these dense nurseries. Even the Sun was once part of such a region, forming from a fragment of a molecular cloud nearly 5 billion years ago. The chemical elements forged in earlier generations of stars, carbon, oxygen, nitrogen and silicon, became part of the dust and gas that formed the solar system. In this sense, every molecule of air, every grain of sand, and every drop of water carries the legacy of the Milky Way's molecular clouds. Viewed from afar, the galaxy's star-forming clouds would appear as faint knots of opacity scattered along its bright arms. They would drift slowly through the disk, moving with the rotation but also evolving on their own timescales. Some would glow softly where young clusters illuminate them from within. Others would remain dark until their stars are born. The motion of these clouds, though complex, unfolds in smooth continuity, driven by gravity and pressure. Each cloud is both ephemeral and eternal in its transient form, eternal in the cycle it sustains. Within their quiet depths, the Milky Way's next generation of light waits patiently, surrounded by stillness and time. Throughout the Milky Way's broad disk, stars are not evenly scattered, but often gather in groups bound by shared origin or mutual gravity. These groupings, known as star clusters and associations, form the galaxy's stellar communities. Some are ancient and compact, their members tightly bound and moving together as a single unit. Others are loose youthful gatherings destined to disperse after only a few 100 million years. Together they illustrate the Milky Way's dynamic balance between connection and dispersal, how stars are born in company, drift apart, and yet remain linked through shared motion in the grand rotation of the galaxy. Two main families of clusters inhabit the Milky Way: open clusters and globular clusters. The open clusters reside mainly in the disk, close to the spiral arms, where star formation continues. They contain dozens to thousands of stars born from the same molecular cloud, sharing nearly identical ages and chemical compositions. Because they form in the dense gas of the spiral arms, they serve as snapshots of the galaxy's ongoing stellar birth. Over time, gravitational tides, encounters with passing stars, and the galaxy's differential rotation gradually pull these clusters apart. Their stars spread into the interstellar field, joining the smooth background population that fills the interarm regions. In this way, open clusters are both temporary structures and vital contributors to the galaxy's stellar population. One of the best-known open clusters, the Pleiades, lies only a few hundred light-years away in the constellation Taurus. Its bright blue stars, still enveloped in a faint haze of reflection. Nebulae are less than 100 million years old children in galactic terms. Another cluster, the Hyades, older and closer, shows what time does to such gatherings. Its stars have spread farther apart, their brightness fading as they move toward independent orbits. Thousands of similar clusters dot the disk, each at a different stage of dispersal. In infrared and ultraviolet light, they reveal the timeline of stellar evolution written across the galaxy's spiral arms. Each open cluster marks a place where gravity and chance combined briefly to hold together the luminous products of a single birth event before the quiet process of separation resumed. Globular clusters, by contrast, belong to a much older and more distant population. They orbit in the galaxy's halo far above and below the disk, following elongated paths that take hundreds of millions of years to complete. These clusters are dense spherical collections of up to 1 million stars bound so tightly that many have survived since the Milky Way's earliest epochs. Their stars are ancient, low in heavy elements and burn with steady reddish light. Seen through telescopes, they appear as glowing spheres, thousands of pinpoints packed together at the core, fading gradually toward the edges. Unlike the open clusters which dissolve within the disk's dynamic environment, globular clusters endure for billions of years, stable against disruption. They preserve a fossil record of the galaxy's formation containing stars older than the spiral structure itself. Associations form a third type of stellar grouping, even looser than open clusters. These are vast spread-out families of young stars that have not yet drifted entirely apart, but are already too diffuse to be bound by gravity. The Orion OB association surrounding the famous nebula is one example. Its massive hot stars illuminate surrounding clouds, shaping the interstellar medium. Over time, these associations dissolve completely, scattering their members through the disk. Although their lifetimes are short, they play an important role in distributing heavy elements and radiation through the galaxy, enriching nearby gas with material from stellar winds and supernovae. They represent the earlier stage of a cluster's dispersal, the transition between birth and independence. The Milky Way contains thousands of clusters and associations at every possible stage of this cycle. Their distribution traces the spiral arms marking where molecular clouds recently collapsed to form stars. Within each spiral arm, young clusters are found near the regions of active star formation, while older ones lie farther downstream, gradually moving away as the galaxy rotates. This spatial progression creates a quiet gradient of age and brightness across the arms. The pattern reflects both the galaxy's rotation and the slow migration of stars through its disk. In the interarm regions, only older clusters remain survivors of generations that formed long ago. Clusters also serve as laboratories for understanding stellar evolution. Because the stars within each cluster formed from the same cloud, at roughly the same time, their differences in brightness and colour reveal how stars of varying masses evolve. Observations of clusters have defined the timeline of stellar life cycles, showing how massive stars burn quickly and fade, while smaller ones endure for billions of years. This knowledge extends across the galaxy, allowing astronomers to estimate its age and chemical history. The globular clusters, with ages exceeding 12 billion years, demonstrate that the Milky Way's structure began forming shortly after the birth of the universe itself. The open clusters, younger and more numerous, illustrate how that ancient framework continues to evolve. The gravitational influence of clusters extends beyond their boundaries. Passing through the disk, they can perturb nearby gas clouds, subtly altering the conditions for star formation. Over long periods, such interactions contribute to the galaxy's slow self-regulation, ensuring that no region remains static. Each cluster, no matter how small, participates in this continuous interplay. The resulting structure of the Milky Way, its spiral arms, gaps, and lanes reflects the cumulative effects of countless clusters forming and dissolving over billions of years. Seen from a great distance, the Milky Way's clusters would appear as points of concentrated brightness sprinkled across the disk and halo. The open clusters would trace delicate threads of light along the spiral arms, while the globular clusters would form a shimmering halo around the galaxy's luminous plane. Their arrangement would resemble tiny constellations within a larger whole, each marking a story of birth, endurance, and decay. From this vantage, the clusters would seem motionless, but in truth they move ceaselessly through space, their orbits weaving together the visible and invisible components of the galaxy. The existence of clusters and associations reveals the cooperative nature of the Milky Way's evolution. Stars are not born alone. They emerge in communities that disperse slowly into the wider disk. The pattern repeats endlessly. Clouds collapse, clusters form, associations scatter, and their stars join the general population, enriching the galaxy with new light. It is a process of continual renewal carried out in quiet harmony. The clusters may differ in age and structure, but all share the same fate to shine together briefly before drifting apart, leaving behind only the memory of their unity imprinted in their motion. Through this gradual dispersal, the Milky Way maintains both dynamism and calm. Clusters form the galaxy's punctuation marks, moments of concentrated creation within an ongoing sentence written in light. Even after they dissolve, their stars continue to orbit peacefully, contributing to the galaxy's glow and gravitational balance. The Milky Way's beauty lies in this steady cycle where order and dissolution coexist, and where every cluster, no matter how transient, becomes part of a greater enduring pattern that unfolds silently across the ages. At the heart of the Milky Way's luminous disk lies an elongated structure of stars and gas known as the galactic bar. It stretches across the inner regions of the galaxy for tens of thousands of light years, bridging the bases of the spiral arms and channeling material toward the central bulge. The bar is not a separate object, but an organized pattern of motion, a vast slow rotation of billions of stars following elliptical orbits that align to form a continuous bar-shaped figure. Through this structure, matter flows inward, guided by the galaxy's gravitational potential. The bar's presence shapes nearly every aspect of the Milky Way's dynamics, influencing how gas moves, how stars form, and how the spiral arms emerge from the inner disk. Yet despite its scale, its motion is smooth and balanced, a quiet current of light and gravity threading through the galaxy's core. The stars that compose the bar are primarily older reddish and densely packed. They orbit the galactic center in elongated paths aligned so that their collective motion creates a distinct bar pattern. Interstellar gas, drawn by gravity, follows similar trajectories, spiraling slowly inward along the bar's edges. As the gas flows toward the center, it compresses and cools, feeding regions of moderate star formation near the bar's inner ends. The process is gradual, proceeding over tens of millions of years, but it continually replenishes the inner galaxy with fresh material. In this way, the bar acts as both a structural brace and a conveyor, maintaining the galaxy's internal equilibrium. Observations of other barred spiral galaxies show that such structures are common in the universe. Roughly 2/3 of all spirals possess central bars, suggesting that this configuration is a natural outcome of galactic evolution. In the Milky Way, evidence for the bar comes from infrared observations which can penetrate the thick dust that hides the inner regions from optical view. These surveys reveal a dense peanut-shaped distribution of stars crossing the core, their brightness tracing the bar's orientation. It appears tilted relative to the sun's line of sight, one end closer to us, in the direction of the constellation Sagittarius, and the other extending outward towards Scutum. The entire structure rotates slowly, completing one full turn every 100 million years or so. The bar's gravitational field affects the motion of stars far beyond its boundaries. It induces resonances in the surrounding disk, altering the orbits of stars and gas clouds as far out as the spiral arms. These resonances may help sustain the galaxy's spiral pattern, linking the rotation of the inner and outer regions into a coherent whole. Where the bar's influence meets the arms, gas tends to accumulate, forming bright star-forming regions that mark the junctions between the two structures. The Scutum Centaurus arm, one of the Milky Way's dominant spirals, appears to originate precisely at one of these intersections where the bar's flow meets the disk. Within the bar, the density of stars is immense, and their combined gravity creates a deep potential well that anchors the galaxy's rotation. Yet the motions remain remarkably orderly. Each star follows a predictable path, its velocity determined by the balance between centrifugal force and gravity. Although collisions between stars are virtually non-existent, their collective movement produces a continuous flowing pattern. The light from billions of these stars blends into a soft reddish glow that dominates the inner Milky Way when viewed in infrared light. The overall effect is one of quiet cohesion, a vast river of starlight turning endlessly around the central bulge. The bar also interacts with the Milky Way's reservoir of interstellar gas. As gas flows inward along its length, it experiences compression and shock where its orbit changes direction. These shocks form faint curved lanes of enhanced density that run parallel to the bar's edges. In these zones, star formation occurs in gentle bursts, producing clusters that illuminate the surrounding dust. Over time, the bar's motion drives gas into the very center of the galaxy, where it contributes to the growth of dense molecular clouds and eventually fuels activity around the supermassive black hole at Sagittarius A. This slow inward drift of matter acts as the galaxy's internal circulation system, transferring energy and mass toward the core while maintaining overall balance. Despite its large scale, the bar is transient on cosmological timescales. Simulations suggest that it forms, strengthens, and eventually weakens over billions of years, influenced by interactions with dark matter and the surrounding disk. Yet within the span of human history, its structure is effectively permanent, a stable guiding feature of the Milky Way's design. The formation of the bar may have begun several billion years ago when gravitational instabilities in the disk caused stars to adopt elongated orbits. As these orbits aligned, they reinforced each other, producing the coherent pattern visible today. This natural self-organization illustrates the galaxy's tendency toward equilibrium. Even in complexity, order emerges gradually and endures. Viewed from above, the bar would appear as a bright central band crossing the galaxy's glowing core, with spiral arms unfurling from its ends like ribbons of light. The inner regions near the bar's midpoint would glow most intensely, a concentration of old stars shining steadily against the surrounding dust. From Earth, however, this view is hidden by intervening clouds of gas and dust along the galactic plane. Only through infrared and radio telescopes can astronomers glimpse its full shape. Even so, the evidence is clear: the Milky Way's bar is a defining feature, shaping the motion of stars and the flow of gas throughout the inner galaxy. The dynamics within the bar illustrate how gravity and motion achieve harmony on cosmic scales. Each star moves according to local forces, yet collectively they create a unified structure that endures for eons. There is no turbulence, only smooth rotation guided by the galaxy's mass distribution. The bar channels not only matter but also energy and angular momentum, redistributing them to maintain balance between the inner and outer regions. It is a stabilizing bridge between the galaxy's spiral arms and its dense core, ensuring that the Milky Way remains both dynamic and serene. If one could stand far above the galactic plane and observe the bar over millions of years, its motion would appear slow and deliberate, turning like a silent wheel within the heart of the spiral. The outer arms would follow, connected to its ends like gentle extensions of its movement. Within this vast mechanism, every star and every cloud of gas plays a part in maintaining the galaxy's structure. the galactic bar is both the Milky Way's foundation and its pulse, a quiet, enduring stream of starlight flowing through the center, uniting the galaxy's outer beauty with its hidden, powerful heart. At the center of the Milky Way, enclosed within the sweeping curve of the galactic bar, lies a dense, radiant region known as the inner bulge. It is a spheroidal concentration of stars that marks the galaxy's oldest and most massive stellar population. Extending several thousand light-years in every direction, from the core the bulge glows with a warm golden hue composed of countless aged suns. It dominates the inner few degrees of the Milky Way sky, its light softened and reddened by the thick bands of dust that obscure direct view from Earth. Though hidden behind these veils, the bulge represents the Milky Way's gravitational and luminous heart, a zone where time itself seems to slow, where orbits compress, and where the combined energy of hundreds of billions of stars merges into a steady, enduring brilliance. The stars of the bulge are ancient, formed in the galaxy's earliest epochs more than 10 billion years ago. Many are small red, and long-lived, their nuclear furnaces burning quietly since the dawn of the Milky Way. Interspersed among them are slightly younger populations that were drawn inward by the galaxy's evolution, captured and mixed into the dense stellar field. The overall motion of these stars is complex but stable. Some orbit the galactic center in random directions, forming a pressure-supported spheroid, while others follow elongated paths aligned with the bar, creating a subtle, box-like or peanut-shaped structure visible in infrared observations. This combination gives the bulge its distinctive shape, not a perfect sphere, but a rounded, textured mass sculpted by billions of years of slow rotation and gravitational equilibrium. The density of stars within the bulge is extraordinary. Near its core, a single cubic light-year can contain thousands of stars, whereas in the Sun's neighborhood, only a handful would be found in the same volume. Yet even in such density, collisions are rare, for the distances between stars remain immense by human standards. Instead, their mutual gravity maintains a delicate balance, ensuring that the region remains stable and long-lived. The light from these stars blends into a smooth radiance when seen from afar, forming the glowing center of the Milky Way visible on clear nights as a soft bulge of luminosity toward Sagittarius. The dust that lies along the galactic plane hides much of this light in visible wavelengths, but infrared observations reveal the full extent of the bulge as it swells above and below the disk. The bulge is also rich in heavy elements, the products of earlier generations of stars that lived and died within its bounds. This chemical enrichment testifies to an intense period of star formation in the galaxy's youth, when supernovae and stellar winds recycled material at a rapid pace. Over time, the rate of formation slowed, leaving behind a mature population of stars evolving quietly. The remnants of this early activity, white dwarfs, neutron stars and black holes, are scattered throughout the bulge, unseen but influential through their gravitational effects. Occasionally, when one of these compact objects interacts with a companion star, it produces bursts of X-rays that momentarily pierce the darkness, offering glimpses into the hidden population of relics that fill the region. Gas and dust are present here as well, though in smaller quantities than in the spiral arms. What remains is drawn inward by the gravitational pull of the bulge, forming elongated streams and filaments that orbit the center. Some of this gas is heated by radiation, and shock waves glowing faintly in infrared and sub-millimeter wavelengths. The rest cools, slowly settling toward the inner regions, where it may eventually contribute to new star formation. These processes occur quietly and continuously, their pace measured in millions of years. Unlike the active turbulent star-forming regions of the outer disk, The bulge's evolution is measured and restrained, governed by the slow rhythm of stellar aging and gravitational settling. The central bulge plays a crucial role in maintaining the Milky Way's balance. Its enormous mass anchors the rotation of the disk, providing the gravitational focus that keeps the spiral arm stable. It also serves as a transition zone between the orderly rotation of the outer disk and the chaotic orbits of the central core. Stars moving inward from the disk gradually lose their planar motion and adopt more elliptical or inclined paths, blending seamlessly into the bulge's isotropic field. This transformation ensures continuity between the galaxy's large-scale structure and its inner gravitational well. Despite the complexity of its motion, the bulge remains tranquil. Over cosmic time, its shape changes, only gradually adjusting to the slow redistribution of mass through the bar and surrounding disk. Embedded within the bulge is a population of massive star clusters and ancient stellar streams, remnants of smaller galaxies absorbed long ago. These relics reveal that the bulge was not formed in a single event, but through a long process of accumulation. As the Milky Way grew by merging with its neighbours, their stars were captured and assimilated, settling into the central potential well. The orbits of these captured stars retain traces of their origins, yet after billions of years they blend seamlessly into the bulge's collective motion. This quiet assimilation continues even today as faint streams of stars, remnants of disrupted satellites, slowly spiral inward under the galaxy's gravity. The light from the bulge defines the Milky Way's most luminous feature. When observed in near-infrared light, its intensity dominates the galaxy's central image, glowing with a steady radiance that overshadows the surrounding disk. From Earth's perspective, this region appears as the dense, hazy core of the Milky Way's band, rich in overlapping clouds of stars. Through telescopes, the bulge resolves into a crowded field so dense that the background never turns dark. Every point of sky contains multiple stars, each one moving independently, yet bound within the same gravitational framework. The collective light of these ancient suns forms a quiet golden sea, a calm luminosity that has persisted since the early history of the galaxy. Within the bulge, the interplay between light and dust creates a soft texture, unlike any other region of the Milky Way. Dark lanes of obscuring material wind through the bright field, casting gentle shadows that give the region depth. Infrared images penetrate this dust to reveal the full continuity of the bulge, connecting seamlessly with the bar and the central molecular zone beyond. The transition between these regions is gradual, with no clear boundaries, only a continuous deepening of density and brightness toward the center. This gradual flow embodies the Milky Way's essence, a galaxy without sharp edges, defined instead by smooth transitions and unbroken motion. If the Milky Way could be viewed from far outside, the bulge would appear as a glowing heart surrounded by the flattened plane of the disk. Its color would be a warm amber, distinct from the bluish tones of the younger spiral arms. From this vantage, one could see the galaxy's internal geometry, the bar crossing the bulge, the arms spiraling outward, and the halo encasing it all. The bulge would stand as the galaxy's visual and gravitational center, a calm core around which everything else revolves. Inside this luminous region, the motion of billions of stars continues silently, their light blending into an unbroken glow. The bulge is the Milky Way's memory, a repository of its oldest stars and deepest gravity, where change proceeds slowly, and where the galaxy's long history is written not in motion but in stillness and light. Moving inward from the bulge, the Milky Way transitions into a region dense with gas, dust and energy, known as the central molecular zone. It occupies the innermost few hundred light-years of the galaxy, encircling the core in a thick rotating ring of molecular clouds and complex chemistry. This zone is unlike any other part of the Milky Way. Here the interstellar medium reaches its greatest density. Magnetic fields strengthen, and the rate of star formation intensifies, though even this activity unfolds in measured periodic bursts rather than constant eruptions. Temperatures are high, yet the overall effect remains one of controlled balance, a deep, steady process of matter, cycling through its most active and most stable forms. The central molecular zone acts as both the heart and the engine of the galaxy's internal dynamics, feeding energy into the surrounding bulge while steadily channeling gas toward the very center where gravity reaches its most profound expression. The gas in this region is mainly molecular hydrogen, but it's far warmer and denser than in the outer disk. Clouds here contain millions of solar masses of material packed into compact volumes, only a few dozen light-years across. These clouds move rapidly, orbiting the galactic center at speeds of hundreds of kilometers per second, yet their motion is well organized, forming an elliptical ring that rotates with remarkable coherence. Superimposed on this motion are intricate flows of gas spiraling inward and outward, guided by the gravitational pull of the bar and the dense concentration of matter near the core. This inward transport of material provides the fuel for new stars and ultimately for the growth of the supermassive black hole that anchors the Milky Way's center. The central molecular zone is a region of contrasts extreme in density and temperature, yet governed by equilibrium. The energy released by massive stars and supernova heats the gas, while radiation, cosmic rays, and turbulence maintain pressure against gravitational collapse. Despite the potential for chaos, the result is stability. The cycle of star formation here proceeds in pulses with bursts of activity separated by long intervals of calm. During each cycle, vast clouds condense and fragment into clusters of young, massive stars that illuminate the surrounding dust. Their light, mostly absorbed and re-emitted in infrared wavelengths, gives the region its characteristic glow when seen by space telescopes. Once these stars reach maturity, their winds and radiation disperse the nearby gas, halting further formation until gravity slowly draws material together again. Among the most striking features of the central molecular zone are its massive clouds, such as Sagittarius B2 and Sagittarius C. Sagittarius B2 is one of the largest molecular complexes in the galaxy, spanning over 100 light-years and containing several million times the mass of the Sun. Inside, dense cores form where new stars and clusters are born. These cores host some of the most chemically rich environments known, with molecules ranging from simple hydrogen cyanide to complex organic compounds. Observations have revealed dozens of different species, hinting at the diversity of chemistry taking place in the Milky Way's depths. Yet even in this chemical abundance, the processes remain gentle, unfolding over hundreds of thousands of years under the quiet influence of gravity and radiation. Interwoven among these molecular clouds are powerful magnetic fields that shape the motion of gas and cosmic rays. Long, narrow filaments of magnetized plasma thread through the region, glowing faintly in radio wavelengths. These filaments stretch for dozens of light-years, standing nearly perpendicular to the galactic plane, and may be among the most ordered magnetic structures in the galaxy. Their presence indicates that magnetic energy plays a significant role in stabilizing the region, preventing large-scale collapse, while guiding the flow of ionized material. These fields connect the central zone to the wider galactic environment, channeling energy outward and maintaining coherence across scales that span from individual stars to the full width of the disk. The radiation environment here is intense but balanced. High-energy photons from massive stars and remnants of supernovae fill the zone with ultraviolet and X-ray light. This radiation ionizes surrounding gas, creating pockets of hot plasma embedded within the cooler molecular medium. Between these zones, layers of partially ionized gas form, where molecules and atoms coexist in delicate equilibrium. The transitions between these layers are smooth, creating gradients rather than sharp boundaries. This layering gives the region its intricate structure, with sheets of glowing gas, dense knots of dust, and open voids where radiation has cleared the surroundings. From a distance, the entire zone would appear as a softly luminous ring, bright in infrared, faint invisible light, and threaded with dark lanes of obscuring dust. Embedded within this environment are massive clusters of young stars such as the Arches cluster and the Quintuplet cluster. Each contains thousands of massive suns, many dozens of times heavier than the Sun, shining with blinding intensity. Their combined radiation carves cavities in the surrounding gas, sculpting the clouds into arcs and shells. Yet even these powerful stars are temporary features in the long life of the galaxy. Within a few million years, they will burn through their fuel, ending their lives as supernovae, and returning their material to the interstellar medium. The heavy elements they release enrich the gas, preparing it for the next cycle of star formation. The central molecular zone thus acts as both a factory and a recycler, turning gas into stars and back again in an endless gentle rhythm that sustains the Milky Way's inner structure. The gravitational influence of the central region ensures that material from the bar and the inner bulge flows steadily into this zone. Simulations show that gas follows long spiral-like trajectories guided by the combined pull of the bar and the central mass concentration. These inflows maintain the supply of raw material even as star formation and stellar feedback consume it. Over millions of years, the net effect is one of balance. What is lost in stars and radiation is replenished from the surrounding disk. The process has likely continued for billions of years, providing a steady heartbeat to the galaxy's evolution. Viewed through the obscuring dust of the galactic plane, the central molecular zone reveals itself only in specific wavelengths. In radio and sub-millimeter light, it glows with spectral lines from carbon monoxide, ammonia, and other molecules. In infrared, it appears as a complex lattice of warm dust and bright clusters. These emissions, though faint to human eyes, convey the rhythm of energy and motion that defines the region. Space-based observatories such as Spitzer Herschel and ALMA have mapped its structure in exquisite detail, showing filaments, loops, and arcs all moving together in a coordinated flow around the galactic center. From a wider perspective, this region represents the Milky Way's inner circulatory system. Gas from the spiral arms enters through the bar, settles into the molecular zone, and eventually migrates further inward toward the central black hole. Along the way, it undergoes transformation through heating, compression, and radiation. The cycle is continuous but unhurried, balanced by the forces of gravity and feedback. The central molecular zone stands as a microcosm of the galaxy itself, dense but stable, luminous but measured, active but calm. If one could watch from afar, the scene would not appear chaotic or explosive, but serenely alive, a quiet core of creation, sustaining the Milky Way's unending motion. At the exact center of the Milky Way, hidden within layers of dust and luminous gas, lies the most massive and enigmatic object in the galaxy, Sagittarius A, the supermassive black hole that anchors everything around it. Though invisible in ordinary light, its presence is known through its immense gravitational pull, which governs the orbits of nearby stars and binds the entire galaxy together. Sagittarius A contains about 4 million times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. It sits in a calm state compared to the active black holes found in distant galaxies, radiating only faintly as it accretes gas at a modest rate. This quiet nature is not a sign of weakness, but of equilibrium. The galactic core surrounding Sagittarius A is dense, dynamic, and bright, yet the motion of its stars and gas reveals a profound balance that has endured for billions of years. The evidence for the black hole's existence comes from precise measurements of stars orbiting close to the center. Over decades of observation, astronomers have traced the paths of dozens of these stars, watching them sweep around an invisible point with incredible speed. One star known as S2 completes a full orbit every 16 years, accelerating to thousands of kilometers per second at its closest approach. The curvature and timing of its motion show that the mass at the center must be concentrated in an object far smaller than any cluster of stars could be. No known force other than gravity acting on such a scale could explain it. These orbits confirm that Sagittarius A is indeed a supermassive black hole, the compact heart of the Milky Way's gravitational system. Surrounding this central object is an environment of extraordinary density and motion. Within the innermost few light years, thousands of stars orbit rapidly, forming what is known as the nuclear star cluster. The stars here are packed closer together than anywhere else in the galaxy, yet even in this crowd there is order. Their orbits vary in shape and inclination, but together they move in harmony under the influence of the central mass. Among them are both old red giants and surprisingly young hot stars, evidence that star formation has occurred repeatedly, even in this extreme environment. How these young stars formed remains an open question, for the black hole's tidal forces make gas collapse difficult. Some may have originated farther out and migrated inward. Others may have formed within dense gas disks close to the center, proving that even near the edge of a gravitational abyss, creation continues quietly. The immediate vicinity of Sagittarius A contains a rotating disk of gas and dust, extending only a few light days from the event horizon. As this material spirals inward, friction and magnetic forces heat it to millions of degrees, causing it to emit faint X-rays and radio waves. Most of the gas, however, does not fall directly into the black hole. Instead, it forms a hot dilute flow that drifts slowly, releasing energy as it descends. The result is a gentle flickering of radiation that varies from hour to hour, the quiet heartbeat of the galactic core. Occasionally, magnetic reconnection or small infall events cause brief flares, brightening Sagittarius A by factors of several before fading again. These flashes reveal the black hole's proximity tracing motions just outside the event horizon, where gravity bends light into arcs and rings. Around this nucleus extends a complex network of molecular clouds and ionized gas shaped by the combined influence of radiation, stellar winds, and magnetic fields. The region known as the circumnuclear disk forms a torus of gas, orbiting a few light years from the center. Within it, filaments of material stretch inward, feeding the black hole intermittently. Other structures, such as the ionized streamers of the mini-spiral trace paths of inflowing gas, illuminated by ultraviolet radiation from nearby stars. These flows move gracefully through the central cavity, their arcs and loops revealing the delicate interplay of gravity and pressure. Despite the immense energies involved, the motion is steady and symmetrical. There are no violent eruptions, only slow transformations governed by the laws of orbital dynamics. Beyond this disk, faint outflows of gas and magnetic energy extend vertically from the galactic plane, forming structures known as the Fermi bubbles, two vast lobes of hot plasma, stretching tens of thousands of light years above and below the galaxy. These are the lingering echoes of past activity from Sagittarius A, likely produced millions of years ago when the black hole was more active. Even so, their boundaries are smooth, their expansion slow. They represent not a recent explosion, but the memory of energy released long ago, now cooling and fading in symmetry with the galaxy's rotation. The very scale of these features conveys calm rather than chaos. Their sheer size ensures that even the most energetic processes unfold gently across millions of years. The gravitational influence of Sagittarius A extends far beyond the immediate core. It ensures that all stars in the bulge bar and disk remain gravitationally tied to the galaxy's center. Without this massive anchor, the Milky Way's rotation would lack its coherence, and the disk could gradually lose its form. In this sense, the black hole functions as the galaxy's invisible keystone, a point of stability, around which every other motion is organized. Yet it exerts this control silently. It does not devour stars indiscriminately or radiate constant fury. Most of the time it rests in equilibrium, its immense gravity balanced by the slow inflow of gas and the steady outflow of radiation and magnetic fields. The Milky Way, as we observe it today, is a mature and settled galaxy, and its central black hole reflects that state of calm. When viewed in radio wavelengths, Sagittarius A appears as a compact source surrounded by faint arcs of emission from hot gas and magnetic activity. Interferometric arrays operating across continents have resolved its silhouette, a glowing ring of light encircling a dark interior where the event horizon hides all. This image, captured through years of careful measurement, confirms that the theoretical predictions of general relativity hold even in the most extreme environment known. The light seen here does not come from the black hole itself, but from gas just outside it heated as it orbits at nearly the speed of light. The resulting glow, bent by gravity into a circular shape, represents the innermost expression of the Milky Way's structure, light curving through space held in perpetual motion by invisible mass. The galactic core, when considered as a whole, is a system of intricate harmony. The black hole, the nuclear star cluster, the circumnuclear disk, and the surrounding molecular zone all interact in continuous balance. Energy flows inward and outward, maintaining the stability of the galaxy's center. Over billions of years, this balance has persisted, allowing the Milky Way to evolve without violent disruption. The star's orbit, the gas circulates, and Sagittarius A remains quietly at the center, a dark anchor wrapped in light. If one could rise far above the galactic plane and look down upon this core, the sight would be both serene and awe-inspiring. At the center, a faintly glowing ring would mark the black hole's boundary, encircled by luminous clouds and densely packed stars. Beyond that, the inner bulge would fade outward into the spiral disk, its light blending into the wider galaxy. The entire structure would appear as a single organism turning slowly its motion, defined by gravity and time. The Milky Way's heart does not beat with violence, but with continuity. Sagittarius A is not a destroyer, but a stabilizer, the still point around which everything turns, ensuring that the galaxy remains whole, luminous, and quietly alive across the vast duration of cosmic history.